Hello. Today we are moving to chapter 11. Chapter 11 is parametric equations and polar coordinates. Let's move to the first section of the chapter, which is curve defined by parametric equations. In this course, we have to cover only two sections of this chapter. Those two sections are section 10.1 and section 10.2. Today we are going to cover 10.1 and then I'll cover 10.2. So this is a curve defined by parametric equations. Let me use a small plot to give you the motivation. Let's say this is a curve that is given to you. Here this is x-axis, that is y-axis, and let's say this is the curve given to you. And let's say this point is xy, this is x, that is y. So this point can be given by x comma y, and this equation can be given by y equals a function of x. For that I use h of x. Alright, this is a curve. We consider a curve as a path of a moving particle whose position is changing over time. All right. So this is you can consider this curve as a path of a particle. All right. This is a path of a particle technically. So current position of the path is right here. The current position of the particle is right here. Then it moves along this blue line. Since this is this particle evolve in time, it evolve in time, so you can just represent this path as a function of t. All right, as a function of t. That means you can write this y. Let me write x first. You can write this x as a function of y, function of t. That means x equals f of t, and then you can write y is also as a function of t. For that I use a new function g of t. All right, this t is in this interval, which is I. Okay, I is called an interval. Let me use a different color for that. This I is called an interval. Okay, you can mark this interval right here. It moves from this position to that position. Okay, so the interval is the time elapsed from that place to this place. Okay, you could consider this as time equals t1 and here time equals t2. So that is the interval actually, t1 to t2. All right. So I assume that you are familiar with this notation. Let me write that notation. This notation means a member. So you could write this as a member. Or maybe let me write as an element. Both are same. An element. All right. If you write something like t in I, That means T is an element in I. That is in other words, T is in the set I. You could say T is in the set I. Okay, so this is extra. All right, so that's how you define the set notation. This is a set notation. This notation is used to define an element. All right, so that means T is in I. T is in the interval I. All right, here T is a parameter and I is the domain of the parameter. All right. Then writing x equals f of t and y equals g of t for the given function. The given function is that y equals h of x for y equals h of x is called parameterization of the curve. Okay, so you know the parameterization now. Parameterization means you have to introduce a parameter like t. Here t is the parameter. Okay, here t is the parameter. Okay, so you have to introduce a parameter here. Here the time is the parameter. All right, so let's move to the first example. You can understand this very well when you do the first example. Example 1. Let's consider this. X square plus y square equals 4. Okay, this is the given equation. You have to find the parametric form of this. So let me write like this. Find the parametric form of this. Alright, you have to find the parametric form of x square plus y square equals 4. Let's check whether you recognize this. Check whether you recognize that. Okay, so that's something familiar to you. You have learned that in Calc 1. Actually, that is the equation of a circle with radius 2. Okay, so that is the equation of a circle with radius 2. Let's consider this as the circle. Okay, and here the radius should be r should be 2. You could consider r should be 2. Alright, so then you could consider this as this angle. Theta is that angle. All right. Now you have to put that into a parametric form. Okay, that means x and y should be represented as a parametric curves. X should be one parametric curve and y should be another parametric curve, like we have seen before. X is one parametric curve and then y is another parametric curve. Okay, that's what we exactly need. Let me write this. This is y, this is g. All right, so let's go forward. Now you can use your trigonometric knowledge for that. You can use your trigonometric knowledge for that. Let me take this part out. That is the radius, which is 2. By using trigonometry, you can write this length should be, the radius is 2, this is 2 cosine theta, and then that should be 2 sine theta. Okay, so these are the equations of x and y. You could write x equals 2 cosine theta, y equals 2 sine theta. Okay, so that is the parametric form of this circle. The parameter here is theta. Now you have to write the range of the parameter, the domain of the parameter. For that theta, how the theta vary? When you just make one circle, theta varies from 0 to, when the point is here, theta is 0, and now the theta is increasing. Theta is 180, 270, finally it is 360. That means 2 pi. Okay, that means theta varies from 0 to 2 pi. Alright, so this is the parametric form of this circle. Okay, let's move to the next example. Example number 2. Compute parameterization of a line passing through the point A comma B with slope M. Alright, so this is the given information. There's a line passing through the point A comma B with slope M. Let me draw this as that line, and it should be passing through the point A comma B, and the slope is just M. Okay, let's take an arbitrary point on this line. Take an arbitrary as x comma y. Alright, so this is that arbitrary point which describe this line, and then you can write down the slope of this line, which is calc 1. You have done this early, so you can make this construction. You can make something like this, and then you could take that as theta. All right, and then slope of the equation is actually tangent of theta, which is the slope equals this, give me a second, this length divided by that length. Okay, so this is, you can take that as h, that is as w, which is h over w. Okay, the height should be y minus b. This height can be given by y minus b because that is the y coordinate. You have to just subtract y coordinates. This is the y coordinate of this point, and that is the y coordinate of that point. So you have to subtract b from y, and this is the x coordinate of that point, and this is the x coordinate of this point. Then you have to divide x minus a, which is w, x minus a. Okay, so this is m. That means m equals y minus b, x minus a. And then you can do something like this. You can just do the cross multiplication. Cross multiplication will give you m times x minus a equals y minus b. All right. Still you have x and y. Now you have to just introduce a parameter. You have to introduce a parameter. For that you could use t. You could use t as the parameter. Introduce the parameter t. Okay. Then you can write m times x minus a equals y minus b equals t. You can write like that. Okay, that's just a representation. Then I write m times x minus a equals t and y minus b equals t. All right, now you have to solve these two equations for x and y. If you solve this for x, it will be x minus a equals t over m, and here y equals t plus b, and here it should be x equals t over m plus a. Okay, so this is the parametric representation of the equation. Let me write it. Parameterization is x equals t over m plus a, y equals t plus b, and now you have to mention how t varies. Actually, t varies for all the real numbers. T is a real number. Okay, you can just substitute anything for t. As you remember, give me a second. Yes, here you substitute t. Okay, t is y minus b or m times x minus a. T can be any value in that case. T can be any real number. So I say t is in R. Okay, I say t is in R. Sorry. This is the parametric equation of the straight line. All right, so let's move to the next definition. Next, we are going to learn a definition. Let me write the definition here. All right, definition. Definition. The graph of any function y equals f of x and sorry, not and. The graph of any function y equals f of x can always be given a natural parameterization. A natural parameterization. Okay, so it's a natural parameterization that I'm going to explain very soon. Let's see what is natural parameterization. Your function is actually y equals f of x, which is the curve you are interested of. All right. Now you can assume x is t. Now let me take this little bit down. Let x equals t in this equation. Okay, then y equals f of t. All right. Thus, the parameterization is x equals t, y equals f of t. See, now you have this new variable t. Okay, now you have this new variable t. All right, let's discuss a quick example here. Let's assume that you have something like y equals x square plus e to the power x plus sine x plus 5. It seems like this is a complicated equation, but it is not so. So you can very easily convert this one into the parametric form. So the parametric form would be you just take x as t. If x as t, y should be t square plus e to the power t plus sine t plus 5. All right, that's it. It's very easy. So this is the parameterization. If you need, you can just write the range of t, that is set of all real numbers. Okay, set of all real numbers. All right. Okay, let's move to example number 3. Example number 3 is is little bit hard. Let me write the example and then I will explain how to solve it. A wheel of radius A a wheel of radius A rolls along a horizontal straight line. Rolls along a horizontal straight line. Find parametric equations. Find the parametric equations for the path traced by a point P on the wheel's circumference. On the wheel's circumference. All right. So first of all, I will draw a small diagram here. Let us assume this is your y-axis, and let us assume this is your x-axis, which is the horizontal line described in this problem. And let's say the disc or the wheel is like this at the beginning. The wheel is like that at the beginning. Okay, let's say this is the radius, which is A. This is x. Sorry, this is y. And let us assume that is x. Okay, so this is the point that we are interested of. A point P on the wheel's circumference. Okay, so that point is right here. All right, now you roll this wheel, and let us assume after some time the wheel will look like this. All right, the point is like this. So this is that point. All right. It was here at the beginning. Now it turned an angle like that. Let's assume this angle is theta. All right, it turned a theta angle like that. Now this is the location of the point. Now you have to write down an equation for that. Actually, it should move like this. It is hard to trace, but it should move like that. All right. So that is the path of that point. Now we have to find a parametric equation for that. All right. So here we have to do some constructions. Do a little bit of constructions. First, you have to understand the replacement of this give me a second. Replacement of this radius. So that is the radius. The replacement of radius is given by that length. All right, so this is actually a theta. You can remember that this length is actually, let me mark it here, this length is equal to that length. All right, so let me mark with a different highlighter. If you mark give me a second. This length is same as that length. Let me use different colors, otherwise it will be confused. You might confuse with those colors. Now it is clear. Okay, this blue length equals that pink. All right, so lengths are equal. To this length are equal. Pink length equals blue length. It's very easy. You can just take a coin and then roll it on the desk. You can understand that. That's how it happens. All right. You have to assume that no slipping between the coin and the table or the flat surface. If no slipping, if you just roll it perfectly on the table, this is what is happening. This pink highlighted length should be equal to the blue length. All right. You know this blue length is actually given as r theta that you have learned in your calculus 1 class. This is actually something like this. You have a circle, okay, and then you have this angle which is theta, and the radius too, which is a, and then you are asked to compute that length, which is this arc length given as a theta is the arc length. Arc length equals a theta. All right, so the same argument over there. All right, so then pink equals r theta. And then you have to understand the rest of the lengths. This length is always a, because that is the height to the center, that doesn't change. And then x displacement is from here to all the way there. Okay, so this is the x displacement. I'm sorry, I made a small mistake here. I should mark, let me mark with a different color. So it goes like that. So this is the x displacement. So that is that, which is x, and then y displacement should be from here to here, which is that. Okay, now you have to compute these small displacements. this displacement plus that small displacement. Okay, they are very easy to compute. This displacement, these black color displacements can be given like this. Let me draw this circle again right here. This angle is theta, and then you have to find this black displacement plus that black displacement. For that you could use you could just compute this angle which is 3 pi over 2 minus theta. So this big angle is theta. Okay, so this small angle is 2 pi over 3 pi over 2 divided minus theta. All right, that is actually this, how do I explain this this entire angle, which is 3 pi over 2 minus this blue color angle. Okay, minus this blue color angle, which is right here. So then the remaining part is 3 pi over 2 minus theta. In that case, you can write this displacement, which equals that displacement, is a cosine 3 pi over 2 minus theta, and then this should be a sine 3 pi over 2 minus theta. All right, which are similar to that and that. All right, now let me write down the complete equation. Then x should be a theta plus, a theta is this plus that, which is a cosine 3 pi over 2 minus theta, and then y should be that plus that. Okay, that means a plus a sine 3 pi over 2 minus theta. All right, let me delete these unnecessary circles. All right, good. So now you have to simplify this. Again, this is calc 1. You know how to solve trigonometric equations. So this can be written down as x equals a theta. As you remember, this part equal to minus sine theta. This part equals to minus cosine theta, that you have learned in calc 1. All right, so let me directly put those values. This is a theta plus a times minus sine theta, y equals a plus a times minus cosine theta. All right, then this can be written down as, further you can write this as x equals a theta minus a sine theta, y equals a minus a cosine theta. All right. Now this is the parametric equation. Now you have to find how theta varies. Okay, here theta varies from where to where. Go back to the original image. This angle theta varies from 0. At the beginning it was 0. Here, let me write it. Here theta equals 0, right? And then when it goes, theta increases. When it goes, theta increases indefinitely. Okay. When you go this way, theta increases indefinitely. Okay, that means theta goes to infinity. So the range for theta should be 0 to infinity. All right, so that is the parameterization. Okay, so let me write one statement, just one word here. The parameterization so this is the parameterization. All right, that is the end of this section. This is an easy section. This section is not so long, but the example 3 is little complicated, so you can read and understand. Here we discussed 3 problems, 3 diverse problems. The section was curves defined by parametric equations. That's all for the day. Thank you very much.